In this video, we're going to learn how to find an equation for a plane given 3 points that live on the plane. So here I want to find an equation for the plane containing the points P, Q, and R, whose coordinates I've given to you. Don't worry so much about the details of those numbers or trying to draw any graph of that accurately. Put that out of your mind, but you do want to draw yourself a picture to help organize your process here. There's a plane I'm trying to find. There it is. And it contains 3 points P, Q, and R, and I've just drawn them roughly at random. Now I'm making a bit of an assumption that my points P, Q, and R are not collinear, and by collinear I mean living on the same line. If 3 points form a line in space, they won't uniquely determine a plane. So I'm taking for granted that they are really kind of arranged in this kind of triangular pattern so that they truly do form a plane in space. If it turns out that they are all on the same line, you'll see something go wrong in the calculation and you'll know that it's not working out. But I think that the 3 random points that I picked probably are not going to be collinear and will determine a plane in space. Now, again, I haven't drawn an accurate picture at all. Don't get carried away with trying to draw really accurate three-dimensional pictures, but it does help me to have this picture because if you recall our discussion about what data help you describe a plane in space, the first thing you probably want is a point on that plane, and I've got 1, 2, 3 points to work with. Take your pick. You can use whichever one you want. That's a good start. The other piece of information that we needed was a normal vector to the plane, and I don't have that in my picture. But if I draw the vector connecting P to Q and P to R, those two vectors lay parallel to that plane. If I want a vector that's normal to the plane sticking out of it, one construction that we have up our sleeve that will do that is the cross product of those two vectors. So if I take PQ cross PR, I'll get a vector sticking up in our picture. You could have done PR cross PQ. It doesn't really matter. We just need any normal vector. But if I do PQ cross PR, I'll get a normal vector to my plane. So we're going to calculate that cross product and use that as our normal vector. So let's get started on that. PQ, I'm going to get by just subtracting the displacement from Q to P. So 1 minus 1 gets me 0, 0 minus 2 gets me minus 2, 1 minus 3 gets me minus 2. So there's PQ. And then I'll do PR, and you can calculate that and check my calculation there, but it turns out to be that vector. We're now going to do PQ cross PR. And to do that, I'll do a determinant expansion. So I'll put IJK up top. I chose to do PQ first. It really doesn't matter here when we're finding a normal vector, but that means I put those numbers first, and then I do minus 1, minus 3, and minus 1 second. I now do this determinant expansion, and I'm going to skip the details here, but just expand out and find the cross product, and you'll find the vector to be minus 4i plus 2j minus 2k. So this vector here is normal to our plane. So is PR cross PQ, the opposite vector. So is anything parallel to this that would be normal to the plane and be sufficient to describe it, but we're going to work with this one. So remember that once you have a normal vector, its components determine the coefficients of an equation for that plane. So one equation for it would look like minus 4x plus 2y minus 2z. That is a linear expression, and it has to be equal to some constant d that I don't know. So this information here on the left-hand side is just coming from the normal vector. That's about how the plane is oriented in space. And then d is going to be somehow determined by the points that it's actually passing through. So if I want to determine d, I just have to use any one of the 3 points that is on this plane that I know. And I'm going to choose the point P, whose coordinates are 1, 2, and 3. And I'm just going to plug them in for x, y, and z. And that's going to determine what d must be. So I'm going to use any point, but I'll use minus 4, 1 plus 2 times 2 minus 2 times 3. And I'm just plugging in those coordinates into my expression. And if you simplify that entire left-hand side, you get d is equal to minus 6. So putting this all together, the points on my plane satisfy the linear equation minus 4x plus 2y minus 2z equal to negative 6. This is an equation of my plane containing P, Q, and R. Now, you probably look at that equation and you say, I don't like all those minus signs, so you might multiply both sides by -1. You get an equivalent equation. The points on this plane satisfy this equation as well. What does that mean geometrically? It just means that the normal vector that you would associate with this equation for -2 and 2 is the vector pointing downwards. It's still normal to the plane. You might see a factor of 2 everywhere. Divide everything by 2. You get an equivalent equation. As long as you do it to both sides, the points satisfying this equation, same plane as the one we were looking for. And this is just a normal vector that's got half the length of the ones that we were looking at before. Any one of these three answers is an appropriate algebraic description of the plane containing out 3 points.